We're looking at Section 7.3 in Chapter 7, Logarithmic Functions. In this lesson, we're going to learn how to apply the laws of logarithms, that is the product law, the quotient law, and the power law. We're also going to use these laws to help us evaluate expressions, logarithmic expressions. Once again, here is a table of the functions we've looked at thus far, Chapter 5, Chapter 6, and of course 7, Chapter 7, the logarithmic function, a natural log function. And we've looked at the characteristics in the equations and the graphs of these functions. In 7.2, we learned how to go from logarithmic form to exponential form. And we see that we have the base of the logarithmic form is the base of the power in the exponential form. The argument is what the power will be equal to. And the last is the exponent. So for example, if we have something log of 27 base 3, that would be 3 to the power of x would equal 27. Using the natural log, which is base e, we have e to the power of y would equal the argument. So for investigating the product law, if you just want to take out your calculator, you can pause the clip, take out your calculator. If you put the number log 24 on your calculator, you should get a decimal of 1.380 and so on. Now if you go and put log 12 plus log 2, you will also get 1.380 and so on. If you put log 6 plus log 4, you will get the same. Here we can see that since 8 times 3 would be equal to 24, the product law says that the sum of two logarithms with the same base is equal to log of m times n. And so we have log 8 base 2 plus log 4 base 2. We can multiply the 8 and the 4. That will give us as a single logarithm log 32 base 2, which we know we could set it equal to x. That would be 2 to the power of x would equal 32. So 2 to the power of x would equal 2 to the 5, and x would equal 5 in this case, which makes sense since we know you can recognize maybe now that the base, since 2 to the power of 3 is 8, this expression will be 3. Since 2 to the power of 2 will be 4, this expression will be 2. And we have 3 plus 2 will give us 5. Let's have a look at the quotient law. If you wish now, you could also pause the clip, put log 2 in on your calculator, and it should give you 0.3010 and so on. Also put log 12 subtract log 6. It should give you the same. And from this, we can see that the difference in the logarithmic expression with the same base is equal to log m over n. Here, since 12 divided by 6 would give us 2, or 8 divided by 4 will give us 2. And so we can look at an example again here. We have log 32 base 2 subtract log 4 base 2. So we would take the 32 and divide by 4. 32 divided by 4 is 8. Now we could evaluate this, set it equal to x, and change it to the exponential form. 2x would equal 8. Of course, and that would be 2 to the x would equal 2 to the 3, so x would equal 3. We're going to see in a little bit here that this is not only setting it equal to the same basis. It's not the only method for solving or evaluating this logarithmic expression. We can also look to see that since 2 to the power of 5 gives us 32, then this part of the expression is equal to 5. Since 2 to the power of 2 will give me 4, this is 4. Sorry, this is 2. So we'd have 5 subtract 2 would give us 3, which is what we obtained. Let's have a look at the power law. If you take the number 1 and multiply it by log 2, you will get the same number as if you take the 1, put it in the exponent, and evaluate log of 2 to the power of 1. This will give us, of course, 0.3010. If we take 2 and multiply it by log 2, this will give us 0.6020, and so on. If we take 3 and multiply it by the log of 2, this will give us 0.903, and so on. Now, if we take and evaluate, we go the log of 2 squared, which is the log of 4, and the log of 4 is going to be equal to 0.602, what we obtained here. The log of 2 cubed would give us 0.903, and so on. And so we can see that the law is you take the exponent and you can put it in front to be multiplied. So n times log m. Here we have 1/2 log 16 base 2, which log 16 base 2, since 2 to the power of 4 is 16, that's really 1/2 times 4, which would give us 2. Another way to look at it is that we have log of 16 to the power of 1/2. It's like taking the square root of 16, which would give us 4. And we know that 2 to the power of 2 will give us 4. So let's have a look at a few examples. We're going to simplify and then evaluate each logarithmic expression. So here, in the first one, we have a sum of 2 logs, and so this would involve the product law. We would multiply 5 by 6.4. And so we have, writing it as a single log, log of 5 times 6.4 base 2. Should be log of 32 base 2. Now, once again, we can continue with the solution by setting it equal to x to evaluate and writing it in exponential form. 2 to the x would equal 32, and of course 2 to the x would equal 2 to the 5, and x will equal 5. Which we could answer that question immediately up here, since 2 to the power of 5 is 32. Let's have a look at the next example. We have here a difference, and we're going to use the quotient law. That will be log of 100 over 4 base 5. This would be log of 25 base 5. Since 5 squared equals 25, then this part of the expression would equal 2. Once again, you could use this method where you're setting it equal to x. We have in the next, in C, example C, we are going to involve the power law. We can bring the 5 in front. That'll be 5 times log 27 base 3. And since 3 to the power of 3 is 27, this part of the expression is equal to 3. So it's going to be 5 times 3, which should give us 15. Here we have, if you just want to attempt these, you have, once again, 2 to the power of 5 is equal to 32. Subtract 2 to the power of 3 is equal to 8. So that would be equal to 2. Let's do this now using the laws of logs. We can write it as a single logarithm by putting 32 over 8. Use the quotient law. This would give us log 4 base 2. And of course 2 to the power of x. If we set it equal to x, would equal 4. 2 to the power of x would equal 2 to the power of 2. So x would equal 2, which is what we have right here. Same for this one. We have, since 5 to the power of 2 is 25, and since 5 to the power of negative 3 is 1 over 125, we have it equal to 5. Once again, we can write it as, using the laws of logs, we could have, writing as a single logarithm, the log of 25 over 125 base 5. This would give us log of 3,125 base 5, which, since 3,125 is 5 to the power of 5, let's still set it equal to x. We can do it this way. Change it to exponential form. 5 to the x equals 5 to the 5, power of 5. So x equals 5. Here we have some more examples. You may wish to pause the clip and attempt these on your own. As you can see, I cannot evaluate each part of the expression now. I do not know what 3, if I set this part of the expression equal to x, I don't know what 3 to the power of x to give me 18. Yet if I use the laws of exponents, I can see that writing as a single log, this would give me 18 times 3/2, using the product law, since there's a sum of 2 logs. This would give me log of 27 base 3. Once again, this would be 3, since if I set it equal to x, this would be 3 to the power of x would equal 27. In B, we have the same concern here. If we set this expression equal to x, you see that 5 to the power of x equals 40. We cannot write 40 as a base of 5. So let's use the laws of exponents. The laws of logs. If we use the laws of logs, we'll use the quotient law here. First, we'll use the power law. So we have log of 40 base 5, subtract log of 2 cubed base 5. So that would be log 40 base 5, subtract log 8 base 5. Using the quotient law, that will be log 40 over 8 base 5. This gives us log of 5 base 5. The answer to that expression will be 1, since 5 to the power of 1 is 5. We can write these as a single logarithmic expression and then evaluate, so we have more examples. Once again, you can pause the clip and attempt these on your own. I will continue. I'm going to use the power rule first. So we have log of 36 to the power 1/2 base 3. Subtract log 2 base 3. And we'd have, this will give us log of 6 base 3. Since 36 to the 1/2 is 6. Subtract log 2 base 3. Using the quotient law, we write it as a single logarithm, 6 over 2 base 3. So this would be log 3 base 3. We can change this to exponential form by setting it equal to x, and the answer will be 1. When we look at the next one, we're going to use the power law here again. Log of 625 plus log of 4 squared give us log of 625 plus log of 16. We can do this one on the calculator since it is base 10, but let's continue using our laws. It says write as a single logarithmic expression and then evaluate. We have log of 625 times 16. This would be the log of 10,000. And since this is base 10, and 10 to the power of 4 is 10,000, this expression would be 4. Evaluating log x base a. So there is another method of evaluating log x base a rather than setting it equal to a variable and then changing it to exponential form. So what we've been doing is we've been looking at things like log 25 base 5, and we would set it equal to x. We'd have 5 to the x equals 25. We could say 5 to the x would equal 5 to the 2, x would equal 2. So this is the method we've been using. But what if we had log of 27 base 5? If I were to set this expression equal to x, that would give me 5 to the power of x would equal 27. Now I cannot write 27 as a base of 5, although I do know that it is somewhere around 2, since 5 to the 2 is 25, and I have 5 to an unknown would give me 27. The answer for x is somewhere around 2. How would I proceed? Well, we can take the log of both sides to preserve equality in equation. So what we would end up doing to evaluate this is take the log of both sides of the equation. So log of 5 to the x would equal log 27. And this log we can evaluate on the calculator. We would move this using the power law here in front, giving us x log 5, which we can evaluate this on the calculator, equal to log 27. Also able to evaluate this on the calculator. Solving for x then, we would see that log 27 over log 5 would equal x. Which now, we have another way of evaluating a log expression. Any log of x base a will be equal to log x over log a, since we're using the method of taking the log of both sides to preserve inequality, of course. So for example, log 27 base 5, as this one right here, that would be equal to log 27 over log 5. So if we're looking at something like this, we have log 9 base 2. This would be equal to, this would be equal to log 9 over log 2. So we can calculate this on our calculator, since it is a log of base 10. And that will give us 3.1699 and so on. Which makes sense, since if the log of 2 to the power of 9, log of 9 base 2 equal x, 2 to the x would equal 9. I know that 2 to the 3 would equal 8, so our answer must be a little bit more than 3. So you can use this method as helping to estimate and check the reasonableness of our answer. In the next one, we have log x base 3 log 11 base 3. That will be equal to log 11 over log 3. And we can calculate this on the calculator. And that will give us 2.18265. Which makes sense since 3 to the x would equal 11. And we know that 3 to the 2 would equal 9. So it must be a little bit more than 2 to give us 11. So now we can keep this strategy in mind. In summary, the laws of logarithms can be expressed as follows, where b, m, n are greater than 0, b cannot equal 1, and b, m, and n are real numbers. We have the product law, which we can multiply numbers when we're given the sum of two logs. We have the quotient law, which we get the quotient of two numbers when there's a difference. And we have the power law, in which we can take the exponent and bring it in front to multiply by the log.